Now, if no, then let's go to the CMOS inverter dynamic behavior. This is the same circuit we have been looking at it a lot of time. Then you know how important it is. I want you to like have it in your mind, imprint it, just like how familiar you are with the inverter, right? If I talk about inverter, immediately you can think about NMOS or PMOS connector. But now when you like to see more, you can think about, oh, there are many capacitors connected together. But the most important is to analyze this circuit, we need to know the condition, right? So what are we investigating here? What we care about is the propagation delay, TPLH, TPHL, right? How the output changes with the input. So you see the input is here, the output is here. So our question is, if my input, let's say, changes from, for example, here, Vin, what happened to my output, right? The output is here, right? It takes some time to go up and then saturate, right? This is V out. This is the question we're asking. So what type of delay is this? Is it TPHL or TPLH for what I just draw? This is a very fundamental question. I actually encourage you to participate, right? That will really make your exam better or your interview better. Trust me. Is it TPHL or TPLH?
The V out curve is TPLH.
TPLH, yeah. From low to high. And what do we measure? We measure for 50%, remember? So this is what we care about from here to 50%, right? So if this is the input pulse is perfect, it is a step pulse, right? Then this one will go step up. You will see something like this. This is how it responds, okay? So then what is the voltage range means? It means that my input go from 0 to VDD divided by 2, right? This is another scenario. What I'm drawing is actually opposite scenario, right? Go from 0 to VDD. This is VDD divided by 2. And then the output is going to have a delay, right? This is Vin. Here, this is TPHL, right? So in this scenario, the Vin go from 0 to VDD divided by 2 in no time. That is our assumption when we do the measurement. Then what happened to output? It go from VDD to VDD divided by 2. Why we choose VDD divided by 2? Again, we talk about 50% to 50%, right? Input changed by 50% and output changed by 50%. So this is the scenario. This one, we only care when you go from VDD to VDD divided by 2 or from 0 to VDD divided by 2. If that is the case, what is the region of operation of M1 and M2 when we are calculating the delay? Right? Let's think about that. Let me just use this one, right? Look, the red. Let's use this one. This is red. This one is already at VDD, right? Because it takes no time to VDD. Okay, but how about this one? This one is still waiting to go from VDD to VDD divided by 2, but it takes times, right? So what I'm asking is right at the beginning of switching, right? This one go from 0 to VDD. Maybe I should write it better. From 0 to VDD, right? Before 0, when it was at 0, this one is at VDD. then it suddenly become VDD. Then it will start gradually change to VDD, gradually change to 0, and you pass through VDD divided by 2. But right at VDD, this one is still at VDD, correct? What is the operation regime for M1 in this case?
Oh, it's on.
It is on because this is VDD. Can you be more specific? Is it linear or saturation?
I think linear.
Let's check carefully. This is VDD, right? How about this point? What is the voltage at this point, at V out at this time, when it starts switching?
It's VDD again.
Yeah. So what is it?
It should be in linear region.
Linear or
Sorry, saturation, I guess.
saturation? Yes.
Saturation, yes.
Very good, right? It's in saturation region. How about for M2? Everyone okay with this? M1, right? Can you please ask question if you don't follow, right? Understand it now better than do it wrong in the midterm.
Professor.
Yeah.
I didn't follow because at the time equal to 0, it should be the gain of the M1 is equal to 0, right?
Okay, I'm talking, okay, very good, right? So I pick an arbitrary time. I'm talking about this time here. Let me call this blue, okay? This is called blue. And I say not discuss. I'm not going to discuss in detail, right? And what I'm discussing is the red one here. Here. Let's call this T or T0. I'm talking about here. So right at T or T0, it takes no time to go from 0 to VDD, right?
Okay.
So that's why it is VDD. Okay.
All right.
Okay. Yeah. And here is also T or T0. Very good, right? So you know, this is very important, right? You ask this question. I really hope everyone do that. Then how about M2, if that is the case? What is the region of operation for M2 at this moment?
It's cut off.
Cut off. Let's see if this is the case. VDD. Here VDD. And here VDD. Exactly, cut off, right? So this is off. Why I want to ask this? Because now, based on this, you decide what are the capacitors for each of these. You remember that the capacitance depends on the region of operation. Okay. So what capacitors we are talking about? This one I say many times already. We care about CGD1, 2, right? CDB2, CDB1, the wire, and then why I care about this one? Because this one is the loading. I need to know what it is trying to drive, CG3 and CG4. Okay, so that set up the scenario, the background. So now our goal for this lecture is to understand what is the delay from V in to V out when I switch from 0 to VDD. And now you know that we have these different capacitors. We also know the region of operation is off for M2 and it is saturation for M1. And now we will calculate this capacitance. Is this okay? Okay, so setting the stage is important, right? Then now the first thing, let's zoom into here, right? You see that I still have this V in and V out. Now my goal is to ask myself, what is CGD12, right? CGD12, of course, we are talking about is equal to CGD1 plus CGD2, right? You have an NMOS and PMOS, okay? So first of all, right, CGD1 due to what component, right? We just say that this is in off state and this is in saturation. Do you remember what is the capacitance for off and saturation? It happened that they are the same. Let's just review what we learned in the transistor. Now, I hope you appreciate why we spend so much time to do transistor. In saturation, we actually don't have capacitance between the gate and drain, except we have a overlapping capacitor, CGDO. Remember? How about in off state? Again, we don't have any capacitance between the source and drain, except the CGDO. So now I'm telling you that CGD12 is CGD1 plus CGD2, right? Remember, this is D. And this is saturation, and this is off states. Then, of course, both of them are due to CGDO times W. Is this okay? Right, that is the first thing. Oh, we know when we are switching, CGD12 is due to CGDO. Okay, but more than that, this comes to the so-called Mueller effect. When we switch the device, we go up in the input and go down in the output. We say that this is equivalent to having a capacitor which is 2 times of the original capacitance in the output. And this is called Mueller effect. I won't go into details, right? We actually usually learn this in the analog circuit. But in general, this is like this. If I have an amplifier with gain A, okay, and then I have a capacitor here. Let's say this is C. And let's say the gain is negative. This one is equivalent to have to something like this. I can decompose this one into 2 capacitors, with this one being 1 plus 1 over A, and this one being 1 plus A times C. Okay, this is Mueller capacitor, right? Have you learned this before? Anyone who has learned this before?
Yes, Professor.
Very good. Okay, any other people?
Yes, sir.
Okay. Now, if you have not learned this before, you forgot, doesn't matter, right? In this class, we don't go even deeper. And I maybe for the sake of time, I'm not going to explain. But basically, is that you have this characteristic. So here we assume the gain is -1. We assume A equal -1. Not exactly correct, but that is a good approximation, because over the whole region, this one and this one approximately give me this. But the most important is that I have a Mueller capacitor, which is 2 CGD1 instead of just CGD1. Okay. So now I realize that maybe this one will give you a little bit of confusion, because we call this one CGD1 here, and it just becomes CGD1. So I think the best is, sorry, I should actually change to another symbol. Just call it CGD effective, right? Equal to this one. So CGD12 will be equals to 2 CGD overlap for transistor 1, W1, plus 2 CGDO2 for W2, right? Is this okay? Basically, what I'm saying is that, okay, this drain cap CGD is just the CGDO of both of the transistor. But because of Mueller effect, they got double. So it becomes CGDO1 W1 plus CGDO2 W2. That's it. Any questions? Now, if no, then let's move forward. I also need to understand what is CDB1 and CDB2. This is highly nonlinear, right? But we learn how to find the capacitor. If you forgot what is CDB, this is the capacitor. If this is source, this is drain, and this is the body. We're talking about this depletion capacitor, CDB. Okay, now how do we calculate it? If you remember, we need to find out the region of operation from what voltage to what voltage. I just told you that this one go from VDD to VDD divided by 2, the output, right? And this is VD. VD go from VDD to VDD divided by 2. But VB, right, is always connected to VDD, and this VB is always connected to ground, right? So for NMOS, what will happen? We say this one starts from VDD, so it goes from, we say that V drain goes from VDD to VDD divided by 2, and V body is 0, right? So VDB goes from what to what? Goes from VDD to VDD divided by 2, right? Because your body is always at 0. So your drain go from VDD to VDD divided by 2. So VDB go from VDD to VDD divided by 2. VDB is the drain to body potential difference. The potential difference go from VDD to VDD divided by 2. How about for PMOS? For PMOS, VDD also go from VDD to VDD divided by 2, right? But how about VB? What is the VB of PMOS, as just said?
It's VDD.
VDD, right? So DB, here I will use VDB. It goes from negative VDD divided, goes from 0 to negative VDD divided by 2. Yeah, so you know the initial, right? So this is the V low, maybe this is, I call it V high. This is V low, remember? This is V low. This is V high, right? Their absolute value. And then we already told you that, hey, their capacitance is just E equivalent times CJ. CJ0 is the built-in capacitance of the junction at 0 bias. And then K equivalent is just this one. You already know what is V high, V low. You know what is M, right? And then we take both sidewall and bottom into account. Then give this one, give us the junction capacitance during the switching. Any questions? Now we learned about this before already, right? Then how about wire capacitance, right? Wire capacitance, you think about yourself. We learned in chapter 4 already. How do we find the wire capacitance? Yeah, you can do RC, but it really depends on whether you use the lump model or the distributor model, right? So this really depends on how important it is, right? If you actually, for example, if let's say dominated by the driver resistor, right? The driver resistance, what does it mean? The driver means the first stage, M2. and M1. Right? If their resistance dominate, then we can ignore wire resistance. Right? Otherwise, we need to use the lump model. Right? Lump model is talking about what? The delay is proportional to the resistance per unit area length times capacitance per unit length times L squared. Okay, and what is the total capacitance? It really depends on the layout, right? It depends on the W, depends on the L, right? And then the unit. So the total capacitance equal to total wire capacitance equal to W times L times unit capacitance. Okay, so here we have not made the decision yet. And unfortunately, in this class, later you will see that I will just say we ignore the wire capacitance. But I want to remind you a little bit. We talked about this already. Driver capacitance. You have a voltage source, right? And then you have this out drive. This is exactly the out. This one is the out drive. You try to drive a resistor, a wire, which has a distributor nature, right? And then you drive to the load. If you remember, we are going to say that the total delay equal to 0.69 R drive times the total capacitance of this. This one has R, C, and L, right? R is the unit length resistance, C is the unit length capacitance, right? This one need to drive this capacitance. Let me ignore the loading, right? This one give one delay. This just like Elmore model. And then another is you have 0.38 of the RC L squared. This one itself has another extra delay. That is how you get the total delay, right? We learned about this before, but just want to remind you. Right, we basically treat this as one delay, one capacitor. To charge up this capacitor CL, I need to have 0.69 R drive times CL, which is just the lump delay. But if this one has enough delay also, the wire, then we also have this distributed delay. In this wire, we also have this extra delay. That's how we get to the wire capacitance, right? You learned this already, but now you see that it becomes useful. Any questions? I don't know if I confuse you.
Professor, just to clarify, so we're having like the distributed delay just because like the wire has that much of an impact on the overall delay.
We have distributed delay because the wire has resistance and also capacitance, and that they cannot be ignored. The wire itself has this delay, which we proved before. Remember?
Yeah, I just wanted to clarify. Okay, thank you.
Okay, great. Yeah, thanks for clarification. Yeah, sometimes I did not hear your question correctly. Forgive me, but it's very great you ask question. Everyone okay with that? If you did see this in the exam, you can write down this equation. If no, please ask, right? So good. We are done with what? We are done with CGD, CDB, and C-wire, right? They are complicated, but we know how to do it. And we have some simple form that can help us to gain insight. How about CG3 and CG4? Once we're done with that, we can calculate the delay. So let's look at CGD and CG4. Now the point is you need to know the operation of the region of operation again. Okay, so again, what should we say about M3 and M4, right? We need to make some assumption. Okay, we assume that, remember our scenario was this one is going from VDD to VDD divided by 2. So this one is going to go from 0 to VDD. That is the goal. But we assume, because we are still charging, right? Since V out is changing and has not reached VDD divided by 2 yet, okay? V out 2 is not changed. This is very important. So it is still at 0 volt. This is not difficult to understand, right? I have an input, okay? You say that you go from 0 to VDD. This is V in. Then you say, okay, then my V out will go from here and then have some delay. This is V out. How about for V out 2? V out 2, it will be something like this. Yeah. But however, what we're talking about is we're trying to calculate this one, TPHL. During TPHL, it is not switching yet, right? Because our definition is not going to switch the V out until you reach VDD divided by 2. So that's why here it is still 0 volt. V out 2 equal to 0 volt. Okay, so this is the assumption that we have. Right? It has not reached VDD yet. So this is 0 volt. Is this assumption okay? But so if this is the case, then it means at the beginning, at least, this is about VDD. The gate input is VDD. The output here is about 0, right? So can you tell me, what is the operation regime for M3? This is VDD.
Saturation.
Say again.
Saturation.
Okay, let's do it clearly, carefully. The gate is VDD, right? The output is 0. What is the? Say again. Linear, right?
Linear, yeah, correct.
Very
It's
good. Yeah.
0.
How about M4? Anyone? Anyone else? What is the region of operation for M4? This is still talking about T.
Is it cut off?
0. Cut off. Because at T or T0, this is VDD. The gate is VDD, source is VDD, so it is cut off. Okay, now this is important. Let's think about how you perform again the gate resistance. Right? In off state, I have this one. In linear state, I have this one. Remember? And it turned out that they are the same. Let's consider one by one. G4 is cut off, right? So when it is cut off, G4 has 3 components. One is CGS4, CGD4, and CGB4. Do you agree? That's just what I'm saying here. When it is cut off, you have gate to bulk capacitance, gate to drain capacitance, gate to source capacitance. But what is the gate to source capacitance? What is the value when it is cut off? Anyone remember? And that is question 4, right? Related to question 4 in the midterm.
It should be CGSO4 times W.
Wonderful. Overlap capacitance times
Yeah.
W. I call it
P.
P. Okay. Instead of 4, I call it P now. Okay. Good. How about CGD4
CGDO4 times W.
times WP, right? How about CGB4
COX times WL.
WP
W.
LP? Yeah, very good, right? So here I don't talk about effective capacitance. Let's just do that. It's not a big difference, right? How about for CG3? Linear. Okay. So what are they? Again, you have CGS4 and CGS3 and CGB3, but you don't have CGB3 because you have this inversion channel blocking it, right? But if you remember, in linear mode, we assign half of the capacitance to source and half to the drain, right? So again, you have half COS WPL, this time is N, plus you have overlap capacitance still, CGSO3 times WN. This is the CGS3. And then plus 1/2 COS WPLP plus CGSO4 WN. No, CGDO3, sorry. Am I right? Any questions? And then you combine together, you see that it is the same as CGS4. Becomes CGSO3 WN plus CGDO3 WP WN, and then plus the half plus half equal to 1, right? COS WNLN. Any questions? It's not about the math that this.
Sir,
Yeah.
it's in CGD3. It should be 1/2 COX WN into LN.
Yes. You're talking about here, right?
Yeah.
Thank you. Thank you. Right. I'm happy that you point out, right? Actually, when I look at the last year's slide, I had some typo, but no student pointed that out. But of course, maybe they just fix it and they don't let me know. Okay, so we are done. We know all the capacitance, right? We know all the capacitance. Then we can do the propagation delay.
Professor?
Yeah.
In the diagram, right? So we are considering CW, and then we are even considering CG4 and then CG3. All right. So, but in for the first stage, CG4 and then CG3 acts as a load capacitor. Why are we considering extra capacitance as CW?
No, here is that we try to combine. CW itself is also a low capacitance because you have a long wire to drive this next stage inverter. So its loading capacitance also has this CDB. We'll talk about later. This is called intrinsic loading. Its external loading has C wire and also CG3 and CG4.
So that's basically because of the routing, right?
Yeah, because of the loading. Because now we want to find the delay. So we want to see how much capacitive loading it has. It present to the first stage.
Okay, got it. Thank you.
Yeah, good. Yeah, good question, right? Ask why we do something. You need to charge up the wire, also need to charge up the link stage so that this one can flip, so your signal can propagate to the next inverter. Okay, so now